So hi, good afternoon. This is where we stopped last time. We were discussing different kinds of brain maps, right? We spent a lot of time discussing some of the visual maps, the orientation map and ocular dominance maps and so on. So now the question is, how do these maps form? What are the underlying mechanisms? So let us look at that a little bit. So these maps are not hardwired. So for example, your first instinct might be to just imagine that they're all genetically hard-coded, right? Somehow when brain develops, all these maps also develop guided by genetic information. But actually, it's not true. Maps are dynamic. They form, right, based on stimulus that the brain receives from the external world, and also driven by some kind of learning mechanisms that shape these maps. So they respond to changing conditions of stimulus. So what are these mechanisms which shape these maps? So let us see that. The first concept we need to understand map formation is the idea of a tuned response. So we have seen in the context of visual neural responses that visual cortical neurons in the primary visual cortex respond to oriented bars. That is, so for example, a neuron can respond optimally to a bar of a given orientation. So in this schematic, you can see that when you present a bar which is perfectly vertical, the neuron responds right with a high firing rate. But as you reduce orientation, its firing rate response goes down. So we ignore the actual timing events of the spikes and just look at the average firing rate and call it the cell's response and plot it as a function of the orientation. You will see something like this. In fact, people have found that this tuning curve can be very well approximated by the cosine formula. So something like cos of theta minus some theta I. Okay, theta is the angle to which it is tuned. That theta is the actual angle of the stimulus of the input orientation. So this function approximates the actual response pretty accurately. Okay, so anyway, this is just a simple schematic. So that's called a tuning curve. That is, the curve tells you what is the stimulus which produces maximal response in the neuron. The next rule is when a neuron adapts to its response, it adapts its response to a stimulus. Its neighbors also try to adapt their responses to the same stimulus. Okay, so let us say initially there is stimulus with some angle. Now this angle could be, I don't know, 70 degrees or something like that. Now let us say neuron A responds to that angle. That is the peak of its tuning curve is at whatever 70 degrees. Now neurons A neighbor, right? A neighbor of neuron A also has a tuning, but that tuning is 0 degrees. So it's at a very different tuning. Now, when you repeatedly present the stimulus with this 70-degree orientation to the brain, neuron A continues to respond to that orientation with a high response. Slowly, you will find that neuron B, which is a neighbor of neuron A, also adjusts its tuning to sort of look like the tuning of neuron A. So it slowly moves away from its original tuning to a tuning which is that of its neighbor, which is A. And why is it like doing that? Because the input stimulus, right, is close to to the tuning of neuron A. So that neuron A influences its neighbors also to adjust their tuning to that of itself. Now there is a kind of a mathematical model called a self-organizing map, which I've covered in another course in the data analysis course, but some of you might have picked it up from some other courses, which is based on this idea. This idea of brain maps has inspired the idea of self-organizing maps, which you study in machine learning and neural networks. So in this model, you have a two-dimensional array of neurons, because as you know, brain maps are two-dimensional arrays of neurons in the cortex. So analogously, in the SOM also we have two-dimensional arrays of neurons. And each neuron is tuned to some bit vector. So a neuron, the input need not be just a single scalar, it can be a vector. And so if the input, so you can kind of model the response of a given neuron, so Y, as something like okay, if X bar is the vector to which the neuron is tuned and X is the actual vector which is presented to the neuron, then this function, this Gaussian function, can very well approximate the response of the neuron. That is, when x and x bar are the same, the response is highest, which is 1. To the extent that x is away from or deviates from x bar, the response goes down. So this is like a tuning curve for the neuron. Only thing is it's an n-dimension instead of just a single scalar parameter. So you can see how this kind of a map, can form and develop and cover a bunch of input stimuli or input patterns coming from the input space. You can use these kinds of maps to as a visualization tool for visualizing high dimensional data. In this example, the map shows a picture of poverty, world's poverty of various nations based on 39 indicators. So you take 39 dimensional vectors, right, that represent various indices of poverty. And the map forms in such a way that each neuron represents one nation or a few nations. And the neurons that are close to each other represent nations which are similar to each other in terms of these poverty indices. Okay, so this kind of map develops automatically just based on those two principles. That is, each neuron. So when a given stimulus is presented, the neuron which has highest response to that input, right, will adjust its weight vector further so that its response to that input will be even greater when you present that input again. Then, in addition to the response of that neuron, which is a winning neuron, you also try to adjust the weight vectors of the neighboring neurons in such a way that their response is also increased, right, in response to the same input vector. So this you do for all the input vectors in the data set. And when you do that, the map learns to map the input data. So now with a simple algorithm like that, you can explain or account for a lot of phenomena related to real brain maps. Although it's a very simple model, there's hardly any biology in it, but you can explain a lot of things about real brain maps. So for example, people have tried to model some aspects of these auditory maps. Of course, auditory maps are very complex. And this example is from auditory cortex of the bat. Now bats, they navigate by projecting ultrasonic sounds. So they navigate by what is called echolocation. That is, they make these sounds, ultrasonic sounds, which we cannot hear because they're very high frequency sounds. And these sounds impinge on a target, and then when they bounce back, when they return back, based on the delay between the emitted sound and the echo, the animal can estimate how far the target is. And also when the sound impinges on the target and comes back, based on the relative motion between the target and the animal, right, there will be a change in the frequency of the returning echo, right? This is obviously the Doppler effect. So based on this, the Doppler shift, the animal can even estimate the relative velocity of the target with respect to itself. So like that, by processing the sounds, the echoes coming from the world, from the targets, the animal can learn a lot of information about the spatial structure of the world. Okay, so now all this is done with the help of a bunch of maps in the auditory cortex of the bat. So here again, just like we have seen in other mammalian brains, we have seen that in the visual system there is a primary visual cortex and then secondary visual cortex and so on. In the bat's cortex also there is the primary auditory cortex and then higher order cortical areas and so on. And they represent very sophisticated properties of these sounds. So for example, there is a part of the primary auditory cortex where, so this is a part of, so you see this is the bat's brain, and these colored regions are different areas in the bat's auditory cortex. This orange region with a pink circle in the center, it kind of looks like a wristwatch, right? So the dial part of it is a pink area, and the tails are like the wristband. Now this is almost like a linear strip of cortex. So the frequencies of the sounds are represented in this linear strip. So here again, at this left end, it is like about 100 hertz. Okay, and in the rightmost end, it's like about 10 hertz. And between, you see that pink circle. So here it is representing a narrow band of frequencies from about 62 hertz to about 60 hertz, and here it is in a circular fashion. So on the flanks, the presentation is more linear, but in the center it is more circular. It is possible that in addition to the frequency, it could also be representing the amplitude of that frequency. Okay, so it's a pretty sophisticated map. So now how can you, so people have tried to model just this simple property of this primary auditory cortex of bats. That is, how can you map frequencies almost in a linear fashion on a rectangular strip of neurons. So for that, in this study by Martinez et al., right in 1989, they have taken a SOM model, rectangular SOM, where there are 125 rows and 25 columns. And each cell in this array represents one number, which represents the frequency. Initially, these numbers are all randomly initialized, and then you take data from like a distribution of frequencies. So the frequency distribution is something like this. Okay, so at the lowest level, you have something like 10 hertz. At the highest level, you have something like 100 hertz. In between, this is like about, let us say, 59 hertz to 61 hertz. So there's a narrow band at which there's a lot of energy. So like this, they synthesize, they create some data set with a distribution like this and train the SOM on that. So initially, the SOM, the frequency numbers inside the SOM are all random. There's no specific order. But after training it for about 500 iterations, so they found that automatically the map reorganizes itself in such a way that the low frequencies are all in one end of the map and high frequencies are all in one end. And in the middle, where there is a lot of energy in this in the sound in the spectrum here, in the middle, in that narrow band of about 59 hertz to 61 hertz, a lot of big area inside this strip, right, represents that narrow band of frequencies from 59 hertz to 61 hertz. But otherwise, on these two flanks, right, there is more rapid variation, a sharper gradient of frequencies. So the thing is, there's a distortion in the way the map is shown, because this whole thing is just one cell. Okay, in the horizontal direction, in the vertical direction, this is just one cell. Okay, actually even smaller than that. So you should actually draw this in a kind of a long rectangular strip, but anyway, there's a distortion in the aspect ratio. So one more aspect of the maps are they are dynamic. That is, the maps change with the usage. That is, as you change the stimulus that you present to the map changes. So an interesting experiment of this kind was performed by Michael Messnick and his colleagues. So these map studies were done in the somatosensory maps, right? We have seen that there are these touch maps, right? So we have the motor maps, right, and the somatosensory maps, which is about the touch. So in the touch maps, so there is a map, there is a part of the primary somatosensory cortex where all the fingers are mapped. Now, obviously, these maps have, they don't have simple geometric shape. The shapes are slightly random. So this region 1 here corresponds to the thumb. Okay, so the region 2 here corresponds to the index finger. Region 3 is the middle finger, region 4 is the ring finger, and region 5 is the little finger. So these 5 regions correspond to the 5 fingers of the animal. And on one side of it, you have a region which corresponds to the palm of the animal. So what they have done this experiment is a slightly cruel experiment. The middle finger of the animal was amputated, was cut off, right? And so then they let the sealed off the brain and let the animal just run around for a few months. After a few months, again they opened the animal and then saw what happened. Now, the moment you amputate the finger, and then you give stimuli to the fingers and look at the responses in the somatosensory cortex. These were the areas that earlier responded to the 5 fingers. So right after the amputation, right before sealing of the brain, when they looked at the responses, the thumb still continued to produce responses in area 1. Index finger still continued to produce response in area 2. But there was no middle finger, so you cannot give stimuli there, right, obviously. And therefore, there is no response. The neurons are still intact because their neurons are alive. But the finger which was sending information there, that was cut off. So the neurons were not getting any information, any signals. So they don't respond. Now, when you activate, touch various points on the ring finger, right, you will find neurons in region 4 responding to that. And similarly, the little finger stimulation gives you a response in 5. This is what you would find right after the surgery, after the amputation. Now, after several weeks, right, the middle finger was cut off. After several weeks, when they studied the responses, right after surgery, it was like that, like this, what was shown in the upper figure. After waiting for a few weeks, when they opened the brain again and looked at the map responses, the maps have changed quite radically. So now when they stimulated the thumb, area 1 responded that there is not much in area 1. But now area 2 has changed a lot. What is area 2? When you stimulate the index finger, the area 2 was originally only, the boundary of area 2 was like this originally. Now that boundary expanded and the new boundary is like this. So area 2 is now quite big. This whole thing is now area 2. Similarly, area 4, so the area 3 was originally not, right after the amputation, area 3 was not responding to anything. But now there is no such thing as area 3 because the finger corresponding to area 3 is gone. Now, similarly, the area 4 was originally like this. Now, the area 4, after some delay, right after these few weeks, the area 4 expanded and then encroached into the original area 3 and expanded all the way to the new area 2. So basically what happened, if you think of them as neighboring plots, the fellow who was living in this plot number 3, he vacated and he demolished his house. Now the fellows who were living originally in area 2 and area plot number 2, plot number 4, they've expanded their houses and completely enclosed in the plot number 3, which is now vacant. Okay, so like that, maps can reorganize a lot based on the simulation conditions. Okay, so this also could be simulated very easily and explained very easily using the same self-organizing map algorithm. So in the algorithm, obviously, they have taken a very simplistic representation of both the hand and the map. So the hand model in the SOM model is like this. So this is a thumb. This is the index finger, middle finger, and ring finger, right? And this is the palm. So basically, these are all points from 2D space, coming from different parts of 2D space. When they trained the map on that, they found that so this is this must be index finger. Like a thumb, index finger, middle finger, and ring finger. This is a palm, and quite similar to what they have found in the real animal, real somatosensory cortex. Now remove the middle finger. What does that mean? Just remove the data corresponding to the middle finger. So in the original case, okay, in the original case, there is a middle finger also, but just to simulate the amputation, the removed middle finger is removed. That means that data is not presented. And without the other data is presented, the map is continuously learning with this remaining data. And when you do that, something. So they originally they presented this model which had 4 fingers and the palm. In response to that, the map learned like this. This is the thumb, the index finger, and middle finger, and ring finger. This is the palm. So then they removed the middle finger. What that means is they trained the map only on these points corresponding to thumb, index finger, and ring finger and palm. They removed these data points which correspond to the middle finger. When they did that, the index finger part encroached into this middle finger part. Ring finger also encroached into middle finger part. Of course, there was a small band in the map where neurons didn't respond to anything. They are some kind of dead neurons and they are not responding to anything. That's something that was found in the model. Right? But the model pretty much captures the kind of properties that were observed in the real experiment. And what is interesting is the model is very simple, right? Quite intuitive, and it was able to explain all these phenomena. In fact, the same model was also able to explain some of the visual cortical maps that we have seen in the last class. Both orientation maps and autonomous maps can be very beautifully explained using this kind of a SOM models. Okay, so next let us come to another very exciting application of these map ideas. It's a very nice clinical phenomenon called phantom limbs. This data is from V.S. Ramchandran's book called Phantoms in the Brain. Now, phantom limb is a very interesting phenomenon. It's a clinical phenomenon. So people with amputated limb very often experience this what is called a phantom limb. They have the sense that they still have a limb that is present, although physically that that limb is gone. That sensation of the existence of a limb is still present, and it's in addition to the limb presence, they sometimes also have excruciating pain. Therefore, it becomes a clinical problem. If it is just a feeling of presence of the limb, then you can just take it as an oddity. I mean, it's not harmful. But when there is a pain, it becomes a clinical challenge. So you have to do something about it. You have to treat it. So you can also have, in addition to phantom limbs, like like amputation because of amputation of a hand or a leg. A person can also have a phantom appendix or a phantom nose, etc. So it poses a serious clinical problem. So it's been mentioned in several contexts in history. So, for example, Lord Nelson, the British admiral, right? He had this painful sensation of fingers digging into the palm. He lost his arm, and so he had a phantom limb experience. Not only that, he used to have the feeling that his fingers of the phantom limb are digging into the palm, and that's a cause of great pain. And he also thought it is direct evidence of existence of soul. Okay, so then this Philadelphia physician called Silas Weir Mitchell, right? He coined the term phantom limb because this guy was treating a lot of American Civil War victims, right? Soldiers who were amputated and they were experiencing phantom limb phenomenon. So this doctor was treating them, and he saw a lot of cases of phantom limb, and so that's where he coined the term phantom limb. There's a lot of folklore surrounding phantom limb because initially people didn't understand what it is and why it is happening. There's a lot of stories that were circulated. So one simple theory is that it is because of wishful thinking. So when a patient has his arm or amputated, that the person badly misses the arm, or wants the arm badly. So this strong desire to have the arm back creates a kind of hallucination. This is what this is one of the theories which is proposed. The another slightly more neurophysiologically oriented theory is that when the arm is amputated, there is a stump that is remaining. So when along with the amputation, you also end up cutting the nerves, right? So those nerve endings now curl up and they get inflamed and continue to send kind of pathological signals. It is these signals when they go to the brain, they create illusion of an arm. This is another theory, which is slightly more neurophysiologically oriented, but still it doesn't hold much water. I mean, it's still a pretty simplistic theory. Okay, why is that? Let us see very soon. So to understand phantom limb, we need to understand again. We need to quickly recap what we learned about the maps, right? The somatosensory maps. So we've seen that there is a map of touch information in the somatosensory cortex in the post-central gyrus. So we have seen that it's like a person turned upside down. So the head and all that is in the lower part of the cortex, and the right feet and all is in the upper part of the cortex. Okay, so there's a map like this, and nearby parts of the body surface are mapped onto nearby parts of the cortex. And one more interesting thing is the map has a deep fractures, deep cuts in it. And because of that, you see in this picture, the face part is very close to the hand part. Okay, obviously in the real body, the face and the hand are very far apart. But in the map, the face and the hand are next to each other. That's something you need to remember that. Now, one interesting experiment that gave a clue to the possible origins of the phantom limb phenomenon is a study by somebody called Dr. Ponce at NIH. So, by the way, Ponce is a part of the brain, but anyway, it's also the name of this doctor, which is just coincidental. So, in these experiments, they've taken animals, monkeys, and they've cut their sensory nerves going from the arm to the brain. Right, as these are dorsal nerves. The dorsal nerves are the ones which carry sensory information from the body to the brain, and ventral nerves are the ones which carry information from the brain to the body. Okay, so you have to be careful. If you just cut the whole nerve, it will cut both the motor and sensory. So you have to cut the dorsal roots precisely to make sure that only the sensory input is cut up, but the motor output is still there. So when they did that for a bunch of animals, 11 years after the surgery, they opened the brain and saw what the somatosensory cortex was responding to. They found that after that surgery, after 11 years gap, when they stroked the hand, right, dead hand in the sense, hand is present, but it's not carrying any sensory information because sensory nerve endings are cut off. So if you stroke the hand, there's no response in the somatosensory cortex. But what is interesting is when the face of the animal is touched, right, the cortical regions which were previously responding to the dead hand, that is that hand, they were now responding when the face of the animal is touched or stroked, which is very interesting, and that gives a clue as to what's happening in phantom limb. The first real clue, breakthrough came in some of these clinical studies, which were performed by Dr. Ramchandran. This was with a patient named Tom. He was a 17-year-old person and a male. And he had lost his left arm just below the elbow, and he had the sensation of the arm in the forearm present. Okay, and so he has a phantom limb. And not only that, he could feel that he could wiggle the fingers. So he felt that he had motor control over the phantom limb, right? Also, he could reach out to objects and grab objects. So obviously, this is a kind of illusionary thing because there's no hand there, but he could have that feeling that he's able to reach out and grab objects. So Ramchandran did a very interesting, simple experiment with this patient. He has taken a cotton swab, a Q-tip, right, which you use to clean your ears. And using this Q-tip, the doctor touched the patient right, at various points and asked the patient, the patient was blindfolded, and the patient was asked which part of the body was being touched. Okay, so when the cheek part of the face, right, the doctor was touching various parts of the face of the patient. When the cheek was touched, this patient Tom felt that the cheek was being touched, and he also could feel a sensation in the missing thumb. That is, he has this phantom limb, right? So the thumb part of the phantom limb was also giving a feeling of being touched. Okay, so that is, he would ask him, like, where am I touching? He says cheek. Then he would ask, do you feel sensation anywhere else? Then he would say that that his missing thumb is being touched. Similarly, when the upper lip is touched, he would say that upper lip is being touched. In addition, the little finger of the missing arm is also being touched. So he could feel sensation in both places, which seems weird because how can you feel sensation in both places simultaneously, right? But that's what he was feeling. Similarly, when the lower jaw is touched, he could find the sensation only in the missing little finger, but not in the lower jaw. So the point is, there is a kind of a complete map of the hand on Tom's face. That is, simulation of different points in the face in Tom's face, right, were mapped onto different parts of the hand of Tom's hand, the phantom limb. So how is it possible? What does it even mean, right? So these are the areas with this is the map of the hand as it is superimposed on Tom's face. So thumb is here, index finger is here, and so on and so forth. Okay. So looks like there are there's one more map. So in addition to the so there is also so when you simulate chest, subject would say chest is being touched. When simulate right shoulder, it's right shoulder. But there is one more map tucked into his upper left arm, a few inches above the line of amputation. So that looks something like this. So we have seen that there is a map of the hand on the face, which is shown here with me, right? Which is shown here. There's also a map of the hand in the upper left shoulder, which is shown here. That is, if you touch this part of the shoulder somewhere here, patient would say, "You're touching my index finger." If you touch this part of the shoulder is fine. Right? It's really there. If you touch it, the patient would say, "You're touching the index finger of my phantom limb," and so on and so forth. So there is so all this looks very strange, right? I mean, why would you find maps of a missing hand on some totally disconnected, unrelated regions of the body? So that mystery becomes quite clear, quite obvious, if you notice the map organization in the somatosensory cortex. Because in the map, in the somatosensory map, the hand is here, okay, and shoulder is right here, right next to it, and the face is here, okay, and you see that just like in the previous case of the amputated middle finger, when we did that, no neurons were responding to the middle finger, but neurons respond to the index finger and the ring finger. They were encroaching right into the area where neurons were earlier responding to the middle finger. So similarly here, you have a patch of the cortex which was originally responding to the hand. When hand is gone, this patch of the cortex is now is kind of jobless. It cannot respond to anything. Therefore, the neighboring regions, which correspond to the shoulder on one side and face on the other side, they expand and encroach into the portion of the map which was earlier responding to the hand. So that kind of explains all these clinical phenomena. So in the somatosensory map, the hand region is flanked by the face area below and upper arm and shoulder area above. So since the area corresponding to the forearm doesn't receive signals anymore, the neighboring areas have expanded and moved in. So this is a very simple explanation to all this change phenomena that we have noticed. Just 1 second. So Dr. Ramchandran also studies a couple of other, many other interesting case studies. He describes them in his book. So in this case, the first case study is a person called Mirabel Kumar. She's born without arms, but she still has the phantom limb sensation, and she has on both sides she has phantom limbs. And only thing is these arms are about 6 to 8 inches shorter than usual. And another interesting thing is when she walks, they don't move; they are stiff, right? And another thing is when she's talking, the arms gesticulate. Okay, so that is one thing. So the thing is when you walk, most of the signals that drive walking come from the spinal cord. Okay, so the phantom limbs seem to be produced by cortex because you've seen this connection between cortical maps and the phantom limb. Therefore, when you're walking, it's mostly driven by the spinal cord circuits. So there's something called central pattern generators inside the spinal cord, it is these circuits that seem to be driving the walking, so they don't seem to drive the phantom limb. So it is frozen while the person is walking. But while the person is talking, then talking involves cortical activity, and also there is, it's somehow recruiting the somatosensory area, and therefore she has a feeling of moving the phantom limb. Another patient called John McGrath, right? This guy is a tennis player, and when he serves in tennis, the phantom limb tries to throw the ball. Since he has only one hand, he cannot throw the ball and hit it with the racket. If somebody throws the ball, he can hit the racket. But when he tries to hit it, his left arm or whatever, his phantom limb seems to try to throw the ball. And once when so the doctor does a simple experiment with the patient. There's a cup on the table, and he asks John to reach out and grab the cup, and with his phantom limb. And when John actually tries to reach out to the cup, this doctor tries to move away the cup. So the phantom limb actually ends up being stitched out to reach the arm, and which caused pain, right? So I think all this seems very, very strange, because first of all, the existence of phantom limb itself is a very weird kind of a phenomenon, right? And now when the person is trying to reach a target, the idea that phantom limb gets stretched and which causes pain to the subject, and all this is pretty strange. So even now, some aspects of phantom limb can be explained using this kind of a map explanation. But a lot of phenomena about phantom limb are still a mystery. And I would think that there's a lot of scope for modeling to unravel a lot of these mysteries of phantom limb. So now let us look at the question of why does phantom limb exist? What kind of mechanisms at the level of cortex produce this kind of an experience? So let us look at that. If you look at the simple chain of command in terms of motor action, the highest command originates in what is called the supplementary motor area. Right? We have seen this in some of the earlier classes. So this sends commands to the muscles for execution. And a copy of this command is also sent to parietal cortex and cerebellum. Right? Let me show with the schematic here. So the motor cortex, right, sends command to the hand, and therefore the hand moves. So this is a basic pathway. Then the motor cortex also sends a copy of the motor command to the parietal cortex or cerebellum. So because there are many such loops. So let us take parietal cortex. Now the feedback from the arm, sensory feedback from the arm, in the form of visual information or somatosensory information, goes to the parietal cortex. Okay, because parietal cortex has the sensory association cortices, and you know that visual and somatosensory, primary visual and primary somatosensory areas project to the parietal cortex. So parietal cortex now knows what is the state of the arm. So the motor cortex sends command to the arm to move from point A to point B. Okay, so the feedback from the arm tells you how far the arm has moved. Suppose it is, right, assume that it is at point A and supposed to go to point B. And instead of going to point B, it has gone to point C, let us say. So it needs a correction. Okay, so how does the correction occur? So the motor command sent to the parietal cortex also makes a prediction as to where would the hand be if this command is executed. Okay, so the parietal cortex, so that is called a forward model. A forward model tells you, all right, where would the limb be when a given motor command is executed. So that is, so you know the predicted position of the arm from this forward model, and you know the actual position of the arm from the sensory feedback. The parietal cortex compares these two and finds out the error between these two, because there can be an error between these two. And that error signal is sent back to the motor cortex. Now, motor cortex then takes a corrective measure, right, and sends a further correction to the motor command in the form of motor command to adjust the position of the hand so that it goes to point B instead of point C. So this loop is very important for this kind of error correction. Now imagine what happens in case of phantom limb or phantom hand. Right, since there is no hand, there is no visual feedback, there is no somatosensory feedback. There is a parietal cortex, obviously, that is present. There is motor cortex. Motor cortex can send a command to the hand, right? But it doesn't go all the way to the hand because there is no hand. But motor cortex sends a copy of the command to parietal cortex. This exists. And the feedback from the arm in the form of visual somatosensory, that doesn't exist. So it finds some error, and that erroneous signal goes to the motor cortex. So you see that the motor cortex might try to correct that error, right, and move the hand. So that error will never be corrected because, right, there is no real hand. So we don't know, right, what should be the correct command to put the hand in the correct position. So there's a potential problem. Okay, so one of the consequence of this kind of a loop, which is not compensated because there's no arm at all, is what is called learned paralysis. So in amputees, a copy of the command signal to the parietal cortex is not matched with the sensory feedback because the the copy of the motor command comes to the parietal cortex, but it is not matched by the visual somatosensory feedback coming from the arm. Okay, so and that can lead to so thing is the motor cortex sends a command, right? The arm doesn't move. It sends further command. The arm again doesn't move. So motor cortex then understands that it can never move this arm. Okay, so because whatever it does, there's no change in the response. Because the feedback doesn't change because the arm itself is absent. The feedback doesn't change. So no matter how much it increases the strength of the motor command, which is felt by the parietal cortex, the feedback doesn't change. Okay, so it keeps on getting signal that no, whatever your command you have sent has no effect on the hand because the error feedback, the sensory feedback is not changing, right? So because of that, the brain seems to lead to leads to something called learned paralysis. So it leads to a stiff, phantom limb. This can sometimes also cause pain. So Ramchandran suggests a very simple experiment to fix this problem by introducing sensory feedback where it was absent before in case of phantom limb. So for this, he uses a very simple setup, which he calls a mirror box. So this mirror box, there is a box, and there is a slot. There are two slots through which you can put hands, and there are two compartments in the box, and there are two entry points into the two compartments, and there is a mirror which separates the two compartments. Okay, so the mirror should be so you can put both your hands. In this case, in case of the phantom limb subject, let us say the right hand is a phantom limb, right? So the left hand goes into the left compartment, and right hand doesn't exist, so therefore nothing happens there. Now the mirror is faced so that it faces the left hand. Okay, so when to the subject now, although the right hand is not present, the subject can see a reflection of the left hand, which looks like the right hand. Okay, so in this schematic, earlier there is no visual feedback, no somatosensory feedback. Because of this mirror box setup, visual feedback is now restored, although somatosensory feedback is still absent. So at least partially sensory feedback is restored. So they tried this kind of a setup and wanted to study the effect of such a box on a phantom limb patient. So they've taken this patient called Philip Martinez. This guy had phantom limb because of the arm was not lost, but the nerves were cut off. So because of that, the arm sensation was gone, and so he was feeling the phantom limb. He was having phantom limb experience. So the person was asked to play with this mirror box setup, right? And So after playing with it for a few weeks, the phantom limb was gone, the feeling was gone, and even the pain that came along with it was gone. So he was feeling the phantom limb pain originally, and when he worked with this mirror box setup, the pain was gone and the phantom limb was also gone. So the phantom limb doesn't have any purpose because you cannot do anything with it really. The only problem, if at all, is the pain, right? And in this patient's case, the pain was simply eliminated by use of this very simple mirror box setup. So what is happening in this case is the visual feedback is restored. Somatosensory feedback is still absent. So now brain is kind of confused. I mean, how is it possible to have visual feedback but without somatosensory feedback? I mean, what kind of a hand is that which can present visual feedback but cannot show any touch feedback? Okay, so the looks like brain got confused and kind of got rid of this whole construct, right, of phantom limb. Anyway, that's the explanation given in the book. So another case study, this guy called Robert Townsend, he lost the left arm 6 inches above the elbow due to cancer. And in this case, the phantom limb had this very strong clenching spasm. That is, person has the feeling like just like Lord Nelson's case. This guy also had the feeling that his fingers are digging into the palm. So therefore, there's a lot of pain was experienced. So again, in this case, also mirror box setup just solved the problem and the pain was gone. Now, so then finally, I would like to say that the maps. So although the idea of map can explain several aspects of the phantom limb, right? And even before, if you look at some of the map description, we have described maps as if they are static. Static in the sense, once a map is formed, it is like a picture of the external stimulus on the cortical surface, right? But actually, brain maps are dynamic in a different way also. Let us look at some examples. So let us look at, the thing is also people have found this kind of maps in the primary sensory cortices, this primary visual, primary somatosensory, and primary auditory to some extent, and also primary motor cortex. But if you go to higher order cortices, people didn't find any maps worth the name, right? Things are a lot more abstract. This kind of a simple map structure doesn't appear. So similarly, people have found that in case of olfactory system, there is a response, there is some kind of a mapping, but it's not a simple static map like what we have seen in some of these maps that we have discussed in these two classes. So let us look at the olfactory system. So you know that to process smell, you have taken smell through the nose and you sniff at it. So your smelling operation actually rides over your respiration operation because you have take air inside for respiration. As a part of that, you just take a sniff at the smell and you sample the smell and you process it. So when you do that, the chemicals of the odor, right, they react with some of the chemicals present in this, some of the receptors of olfaction, which are present at the top of the nasal cavity. So here, depending upon the chemicals that are present in the smell, in the odor, right, they are converted into electrical signals, which are now processed by a small structure called the olfactory bulb, which is located right here at the roof of the nose. Now, the olfactory bulb converts it into neural signals, and then neural signals are sent to other, parts of the brain called, piriform cortex and hypothalamus, and so on. Okay, so this is just a simple schematic of the olfactory bulb. This is the nasal cavity, right, and the olfactory epithelium where the receptors which convert the smell molecules, right, the smell chemicals into electrical signals. So now when you present a smell, right, normally if the olfactory bulb acts like a simple map, what you would expect is, right, there is a 2D map, right, if I present smell number 1, okay, neurons here should be active, and smell number 2, neurons here should be active, and so on and so forth. This is what you expect if it is simple map. But actual response doesn't look anything like that. So in this picture, you are seeing the response of the olfactory bulb to air, that is no smell, and the bottom one is to amyl, some chemical, okay, some organic compound. So they repeatedly present the same chemical, okay, to the bulb, and look at the response. In this case, the response is measured not from just one neuron, but they place a 2D array of electrodes on the olfactory bulb and measure the bulb's activity. This is over an area of about 3.5 by 3.5 millimeters. So when they measured that, they found that the response of the bulb to the smell is in the form of a spatio-temporal wave. So again, I can think of this as I of x, y, t. The response which varies with respect to the space and also time. Okay, it's like it's like throwing a stone in a still water. Right? The lake water is still, and throw a stone at some point. Right, depending upon where the stone falls on the lake, it will create a ripple pattern which is characteristic of that position. Okay, so similarly here, depending upon the smell that is presented to the olfactory bulb, it produces a characteristic ripple pattern, a spatio-temporal wave in response to that. So this is quite different from what we would imagine when there's a map structure. That is, every stimulus produces a response in neurons of one part of that spatial map. In case of olfactory bulb, it's not like that. Similarly, even in case of motor map, so it is not that simple as what we have seen before. That is, some of this data has been known for almost a century now. That is, this paper by a guy called Forster, 1936. Forster has written just about the time when Penfield was doing his seminal experiments on brain mapping. So whereas Penfield has popularized a simplistic picture of motor maps that different parts of the motor cortex control different parts of the body. It's a very simple mapping between motor cortex and the various parts of the body. Right? Forster found it's not as simple as that. So he says that a single part of the body, let us say the thumb, is represented preponderatingly, that is primarily, in one part of the cortex, but is represented in other parts of the precentral convolution as well, although in a different degree and in different combinations with other parts of the body. So to make it concrete, right, it says that if you want to control your thumb, it is not being controlled just from one point in the motor cortex. There will be many regions in the same motor cortex which control your thumb, right? If that is the case, then it's not a map anymore. Map means one region in the brain corresponds to one body part. That's a map. But if many regions in the motor cortex control the same thumb, that's not a map anymore, right? So, but this is closer to reality. Similarly, he gives one more an example. A given spot of the thumb focus is stimulated repeatedly at intervals of 1 second by galvanic threshold stimuli. Okay, so here they pass current. So they found that if you stimulate the motor cortex at some point, it produces movement of a thumb. Okay, and you have to pass sufficient current, that is called the galvanic threshold. When they do that, the thumb moves. Okay, so the only thing is they give the stimulation repeatedly at intervals of 1 second. So the first, second, and third and fourth stimulations result in the movement of the thumb. So in that sense, it's like a thumb region in the motor cortex. But what is interesting is, on the fifth stimulation, this movement is fading. The thumb doesn't move anymore. The same thumb doesn't move anymore. The sixth stimulus produces not a movement of the thumb, but a movement of the index finger. So this is very strange. Stimulation at the same location for the first 4 trials produces movement of the thumb. For stimulation at the same location, right, for the 6th trial, produce movement of the index finger. So it's a different output. Again, the same thing happened when they stimulated for the 7th time. But on the 8th stimulation, all fingers except the thumb move. Okay, then on the 9th simulation, the fingers movements are hardly visible. So it's a very strange result because, right, the map picture says that given part of the cortex is mapped onto given part of the body. But here it is not like that, right? The relation between cortex and the body part is quite history dependent. It keeps changing. So the map is quite dynamic. Then on the 10th and 11th simulations, the hand moves, right? And on the 12th simulation, the primary effect, the movement of the thumb, reappears and is obtained by subsequent stimulation. So it's basically all over the place. Okay, so the simple picture of the map, right, that has been popularized in the earliest studies, it's not quite close to reality. Maps are definitely present in the primary sensory areas, especially visual, somatosensory, and auditory. But beyond that, the maps are somewhat weak. They don't appear in such a dramatic, simplistic fashion. Now, the temporal aspect of the map is shown in different aspects also. Now, suppose I'm looking at this picture, like a person standing next to a cat. Okay, so now visually, this person is processed by a bunch of neurons, the cat is processed by another bunch of neurons. So what happens is all the neurons which process the person, right, these neurons fire in synchrony. You see that this is the person. Then all the neurons which fire in response to the cat, right, they also fire in synchrony. So it is not just some bunch of neurons respond to a given object, right? The firing pattern of the neurons also identifies the object through synchrony. Okay, so there is a temporal aspect which encodes information. Now this is nicely captured by what is called a rubber hand experiment. So in this experiment, the subject is sitting here. The green shirt chap is subject, and the person whose head we can see and whose face we cannot see, that's the experimenter. Okay, so in this case, the subject's right hand is visible to the subject, and then there is this rubber hand. You see that white thing, right? And there's a hand at the end of it. That's a rubber hand. And the subject's left hand cannot be seen by the subject because there is a screen. Okay, that the screen between the subject and the subject's left hand. So what the experimenter is doing is, he is gently stroking the index finger of this rubber hand with a brush. Then he is also stroking the actual left hand of the subject also with a brush. Only thing is making sure that these two stroking patterns or stimulation patterns are in synchrony. The individual patterns are quite complex, but the two patterns, the temporal patterns of stimulation, apply to the rubber hand index finger and to the actual left hand index finger. Both these stimulation patterns are in sync in time. So what happens after some time is, suddenly the experimenter gets up and takes a big hammer and bangs on the rubber hand. The subject has a huge shock and has a startled response, and in fact jumps back in alarm at that stimulus. Because so what happens is the subject becomes so deeply identified with the rubber hand, he almost starts thinking that it is his original hand. Why is that? Because his original hand is receiving information, right? The touch information from the experimenter, and the rubber hand is receiving visual information from the experimenter, which the subject is processing. Now, both the stimuli, the visual and the touch stimuli, or tactile stimuli, are very different, but they are in sync. Now, brain believes that whenever two things are in sync, they are coming from the same source. They are coming from the same object. Okay, so the subject's brain kind of is tricked into believing that the rubber hand is his own hand, is identified with his left hand. So therefore, when the experimenter then gets up and bangs the rubber hand with a hammer, the subject has a huge shock. So there's all these temporal aspects, right, in terms of correlation, which can influence your the kind of model of the world that you construct. It cannot be explained simply in terms of static spatial maps. But all this really gives rise to very profound questions, because if all that it takes, right, for us to create an illusion in your mind, right, is to produce these artificial correlations, then you start wondering what is really out there, right? If my beliefs about the world can be modified and distorted so easily, right? What is really out there? Start thinking. Okay, so some conclusions. Brain maps are shaped by self-organization mechanisms, and we have seen visual maps, noticeable maps, and auditory maps. We also seen phantom limb phenomenon. Then we have also seen that there's a whole temporal aspect to the maps, and the classical maps are present only in certain primary sensory cortical areas, and they're not universal. And there are a lot of temporal aspects to understanding maps. So the classical picture is not quite accurate, but it has a limited application. So let us stop there. In the next class, I want to look at either neurobiology of memory or emotions. I'll take one of them. We don't have much time. Next class is exam. So next week, we'll start discussing neurobiology of emotions. So that's all for now. If you have any questions, I can answer.